Hello there. So this is video number 1 of section 4.7. So we're going to go over, I think, a very cool sort of theoretical concept that we can sort of, now that we have this idea that we, in Rn, we can have, many different bases, right? Of course, any set of n linearly independent vectors in Rn gives us a basis. And we've got, now these coordinate representations, right, of these vectors, which, as we learned, define one-to-one maps, right, from Rn to itself. So that is, right, for this vector x, its b representation will be different from the b representation of any other vector of length 2. What we're going to learn here now is how to sort of relate, if I've got two different bases b and c, the b representation and the c representation of a particular vector x. I claim we've actually already seen this a little bit in section 4.4 when we were relating the standard basis 1, 0, 0, standard basis e1 through en to a single other basis b. But here we're going to sort of step back and allow ourselves to look at two bases, neither of which are the standard basis. So this is some, as I put it in the worksheet, some really cool math with some really uncool notation. So yeah, we'll jump right into it. I also, if you are interested, there's these TED Ed, like the TED Talk people, always put up, they put up these really cool like riddles, a lot of which are very mathy, and so I find them very fun. And so I'll often, like if I've got a few minutes, I'll watch one and try to work it out. And so I posted a link to one in particular that I was working on yesterday that I thought was fun. And so if you want to talk about it, certainly I'm happy to discuss it. I did figure that one out. I definitely don't figure them all out. Sometimes I'll just watch to the end of the video for the solution, but it's really fun. I'd recommend checking it out. So I'm going to start out with this problem. So we're given a vector x equal to 6, 3, and we are given two bases, b, which is the vector 1, 2, and the vector 7, 5, and c, which is the vector 0, 1, and negative 3, 1. So remember 1, we want, so first off, we're going to calculate now the b representation of x. And so remember, this is equal to the vector, we'll say, what variables should we use? Y's. We'll go y1, y2, such that x, right, so this vector 6, 3 is equal to y1 times b1, or here we'll call this b1 and b2, plus y2, b2. And so remember, it's just the coordinates we put on these vectors when representing x as a sum of these two vectors. And again, which we know we can do because b is a basis. And so remember, we can end up finding this by just solving the matrix equation. 1, 2, 7, 5 times y1, y2 is equal to 6, 3. And so to do this, remember we row reduce the augmented matrix. And at least from now, I will, there'll be sort of a lot of stuff going on, so I'm going to quickly just fast forward to the solution after row reducing. So I get that that's the row reduced matrix. And so that means that x sub b should be equal to negative 1, 1. All right, so what does this mean? Well, we should be able to check this, right? So if this is the correct solution, we should be able to show that the vector 6, 3 is equal to negative 1 times 1, 2 plus 1 times 7, 5. I think I worked this out beforehand, so hopefully this is correct, but we'll double check. 7 minus 1 is 6. 5 minus 2 is 3, so we're good. So this is sort of like a straightforward, if you're given a basis, an x, and you want to calculate its coordinate vector, this is how you would do that. And so I'll put the solution here. I'll erase the work for now so that we have room to talk about number 2. So we want to now calculate x sub c, but we don't want to do it in the way we just did. Right, so notice you could calculate x sub c in the exact same way we calculated x sub b, except using c as our basis instead of b, right? But what I want to do is use the b representation of x, or show how we can use the b representation of x to calculate the c representation of x. And so I'll explain a little bit why we're going to do this, because like I said, this will seem like another one of those things that's like, well, doing this, on its own is much easier. But so, for one, we might actually run into cases where, maybe we don't know what x is, we just know what the b representation of x is, right? So for example, if I didn't give you x, right, how could you calculate x sub c from x sub b? On top of that, let's say we had, many, many vectors, and we only had their b representations. So we had, some basis that we were working with in some sort of applied problem, and we needed to change bases, right? So we wanted to change from B1 or basis B to basis C. And this type of problem, really does come up in applications. So, and we know the B representations of a bunch of vectors, and we want to be able to quickly change their B representation to their C representation. The solution to this problem will sort of give us a little bit of insight as to how to do that. So we're going to show how we can calculate x sub c only knowing x sub b. So pretending for the moment that we don't know what x is, and that we didn't just do a slightly easier way of doing it, before. All right, so we know that now x is equal to -1 times b1 plus 1 times b2, right? So this is the sort of b representation of x. We also know the following two things, and we'll go over, I believe, next video, what we do if we actually don't know these next two things, but we'll sort of assume for the moment that we know the C representations of both B1 and B2. Right, so notice what these two equations are that I've just put on the board are the B1 and the B2 representations under basis C. So right, this is writing my basis vector B1 in terms of the two basis C vectors. And so what these are, so each of these shows that the following two things, that we know B1, its C representation is the vector 7, 3, and B2, its C representation, oops, sorry, there should be some fractions there. 7, 3, negative 7 over 3, negative 1 over 3. And B2, C is 22 over 3, negative 7 over 3. And I think green is maybe a little too light, so I'll just quickly rewrite those in a color that's easier to see, because this is important. Sorry about the slight delay here. I thought I could get away with writing these in green to sort of differentiate them a little better, but looking at it, it looks like green is a little too light. So there is two vectors that I wanted to write. So what this is, again, it gives me the C representation of B1 and the C representation of B2. So if we know these two vectors, we can use this equation along with these two equations to solve for x in terms of C1 and C2, right? Because what I can do is now just rewrite x as -1 times 7 over 3 C1 minus 1 over 3 C2, right? So I just substituted this in for B1 plus 1 times 22 over 3 C1 minus 7 over 3 C2. And then doing a little bit of rearranging, we can rewrite x in the following way. We get that x is equal to 5 times C1 minus 2 times C2. And so this means that, and actually I'll write it up here, x sub c is equal to 5, -2. All right, so was there an easier way to do this? Or maybe the other question, was there a matrix way to do this? Because linear algebra, matrices, yeah. The answer is yes, because matrices actually, so sort of substitutions like this are made shorter by matrices. So let's see. So notice that if I take the following matrix, whose columns are given by the B representations under my C basis, and multiplied by, so notice what we actually did to calculate this vector was sort of multiplied these two matrices, this matrix by this vector, right? So if you sort of look at this expanded product here, right, this coefficient of 5 comes from -7 thirds times -1 plus 22 thirds times 1, which is exactly what's happening here. Same with this, -1 third C2 matched up with -7 thirds, or sorry, -1 third times -1 C2 matched up with -7 thirds times 1 C2 gives me a coefficient of -2. So notice that this is the B representation of x. This is the C representation of x. And this is the matrix, which I will define in a second, whose columns are given by the C representations of B1 and B2. And so it turns out, if we can find this matrix, we have a really quick way, as we saw here, from going from the B representation of a vector to the C representation of a vector, because it's just matrix multiplication. And so the matrix we calculated here is called a change of basis matrix or a change of coordinates matrix. So here comes, I think, my least favorite notation in all of linear algebra. The notation we use for the change of coordinates matrix. All right, so turns out that what we did here is sort of an example of a larger theorem. That we can actually generalize to all of Rn. And so we're going to let B equal, now we'll just sort of generalize this, some basis for Rn, and we'll let C be a different basis for Rn. And so notice here now, B and C are not necessarily the, right, they're not necessarily the, neither one is necessarily the standard basis. And actually, I said Rn, but this theorem can actually be applied to any vector space V. So we actually can, and we'll see an example where we do expand this to the polynomials later. So we're allowed to consider just an arbitrary vector space V in this theorem. So then we know, and this matrix is the change of coordinates matrix, which I'll define after the theorem. Then there is a unique n by n matrix, which we will denote P sub B left arrow C. It's great notation. Such that basically this matrix takes the B representation of a vector and gives us the C representation of that same vector. Right, so notice here, this matrix is exactly this matrix. So I'll quickly fill that in now. So this matrix here is the change of coordinates matrix from B to C. So how did we find the change of coordinates matrix in this example? Well, we took the C representations of each of our B vectors, and it turns out that this is always how we find our change of coordinates matrix. So notice here, the change of coordinates matrix P from B to C is always the matrix whose columns are given by the C representations of our B vectors. So that is, solve for each of the B vectors in terms of the C vectors and make those your columns. So I'll now formally define this. So this matrix is called, so I prefer the term change of basis. Your book, I think, uses change of coordinates. So if you see change of basis or change of coordinates matrix, those are meaning the same things. And I think I'll try to keep the notation as consistent as possible. So since your book is using change of coordinates, I'll do my best to use change of coordinates as much as possible. But I know occasionally I'm going to accidentally say change of basis, because I think change of basis is a better term because we're changing bases. So, but change of basis, change of coordinates, same thing. All right. So if there's a change of basis matrix from B to C, then there should also be a change of basis matrix from C to B, right? So we'll make sort of another side box here. So we want to ask the question, what is this matrix? Right, so this theorem we're doing B to C, but we should also be able to do it the other way, right? That if we start off with a C representation of a vector, we should be able to work our way back the other way and get the B representation. Well, and so this is the example to the first exercise here. So let's take this equation or keep this equation in mind. Notice that by definition, this matrix, right, should do the opposite of what the other matrix was doing. So this matrix should start off with the C representation of a vector and send it to the B representation of a vector, right? So notice how P sub B to C is doing the opposite of P sub C to B, right? So taking C, sending it to B. Here we're taking B and sending it to C. Okay, well, the two vectors on either side of these equations look the same, right? So x sub C, x sub B, x sub C, x sub B. So how could we calculate this? You know, let's say maybe I've calculated this one matrix and I don't want to go through all of the process of calculating this other matrix. Well, notice the columns of this are all basis vectors, right? And so they're not quite B basis vectors, but they're C representations of B basis vectors. But what do we know about basis vectors? Well, we know that basis vectors are linearly independent, right? And it turns out that the C representations of those vectors are still linearly independent. So that means the columns of this matrix are linearly independent. And so it actually turns out that if I have the change of basis matrix from B to C, its inverse is the change of basis matrix from C to B. So that is, this matrix, P from C to B, is equal to P from B to C inverse. And so if I have this matrix, I can just calculate its inverse to find the other one. So keep that in mind. I'll bring that up in an example later on in the next video. So this is a change of basis, change of coordinates matrix. I want to end with one more example, very similar to the one I initially presented in this video, basically where you're given the same information and you just have to go through all the same steps again. So I actually would highly recommend at this point pausing the video and working through the example on your own, using the steps sort of outlined in the first example. Basically, all this example is doing is walking through the same steps as the first example, but using the new notation we now have. And then, so pause the video, try the example on your own, or if you don't have the worksheet in front of you, certainly I'll write the example on the board and then pause, and then I'll go over the solution. So we're going to be in R2 again. So we're going to let B be the following, well, B1, B2, and C will be the basis C1, C2, B bases for a vector space V. Yeah, and I guess what's cool about this, right, is that we can think of this like R2, but we can actually, from what we've learned so far, we know we can be talking about any vector space V of dimension 2. And so what's cool about this, we're not even going to ever learn exactly what these vectors are. All we're going to know are the following three things. That B1 can be written as a linear combination of C1 and C2, as so. That B2 can be written as a linear combination of C1 and C2, as so. And that we've got some vector x that can be written as a linear combination of B1 and B2, as so. And so notice again, we could solve this by substitution, but since it's linear algebra, we'll solve it with matrices. And so we want two things. We want the change of coordinates, or change of basis if you prefer, matrix from C to B. And then we want the C representation of x. So, like I said, pause the video here, try A and B on your own. All right, so part A, so this is another one of those problems which turns out to be maybe almost easier in a way than we think it should be. Because in this case, we're actually presented with the matrix, just not maybe in matrix form. Oops, I looked at the wrong two. The matrix should be 9, -2, -4. Right, because we've got the C1, C2 representation, and so remember, by definition, this is just the matrix whose columns are given by the C representation of B1 and the C representation of B2. And so this is it. This is the answer to part A. Well, and then we actually know at this point that part B isn't too much harder, because this is just the B to C matrix times the B representation of X. And so this is the matrix 6, 9, -2, -4 times the vector -3, -3, +2. And so multiplying this out, you should get 0, -2. And that would be your C representation of X. Yeah, and so that's this sort of a problem where if we're given the C representations of these vectors B, we just have to put them in the right place in the matrix, make sure that we've got, make sure that it's B to C, put them in the right place in the matrix, and then do some matrix multiplication to change the basis representation of X. All right, so next we'll look at a few examples, one of which in particular gives us a method to basically do this same problem if we aren't presented with 1 and 2. So we'll be given maybe a little less information, but we'll see it's still, so we can still sort of work through this type of a problem.